Okay, thank you. Right, so the idea is that we have, in a gauge system, we have some kinematical Hilbert space, which contains the physical states as a subspace, but also some redundancy. And there, the physical states are invariant under gauge transformations. And now putting these two images side by side, the identifications we make are sort of clear already. One thing I'll have to mention here is that for this talk, I will assume that G is compact. So we just identify the physical space in which we encode quantum information as the kinematical space. We understand the code subspace as the space of physical states in the gauge system, and then the gauge group plays the role of a stabilizer group. Now, the important question to ask is, if we make these identifications, what kind of errors can such a quantum error correction code correct? And for this, we just use the idea of syndrome measurements that we get from stabilizer codes and apply them to our gauge system. So our Hilbert space decomposes into the different charge sectors, HQ. And now we imagine we start with some physical state psi, and some error happens. And this error might map this state into something which has support spread over all of the different charge sectors. Now, if I can somehow measure in which charge sector I am, this will collapse my state into HQ. And then what I want is to somehow map this state back from HQ into HFIS. So what I need for this is an operator which maps from HFIS into HQ and then take its adjoint. So I want to find these operators AQ, apply the adjoint such that this maps me back into my physical space. And then I will get this state AQ dagger pi q e applied to psi, up to normalization. Right, okay, but now this only corrects the state if this state that we ultimately get is up to normalization the same as psi. Then we have corrected our error E. So this protocol that I just described can be summed up as this quantum channel. And the statement we can make is, if we can find such a set of AQs which are unitary on the kinematical space, then this channel is a recovery channel for the error set given by these AQs. And due to linearity, for any other error set which is obtained by these AQs through linear combinations. Okay, so here this charge sector measurement plays the role of a syndrome measurement. Now, what's not clear is whether such AQs even exist or how to find them. Like maybe in a finite dimensional case, it's possible that HFIS is larger than HQ, and so no unitary on HKIN might take HFIS into HQ. So when do such operators exist? And here is where quantum reference frames come into the equation. So because of our setup, where we have a gauge group, I'll be using perspective neutral quantum reference frames, because these just offer a very convenient way of splitting our kinematical degrees of freedom into a set of redundant ones and into a set of physical ones. So, okay, let's start with this structure where our kinematical space splits into a reference frame and some residual system, and so does our gauge transformation. Because I assumed that G is compact, I can write the projector onto the physical states as this coherent group average. Okay, now for R to actually work as a quantum reference frame, I want to somehow parameterize the group action G. So I introduce these orientation states, which transform covariantly and which resolve identity on my frame R. Okay, and if I have such a setup, then I can treat HR, the quantum reference frame, as redundant, and I will be able to map all of the physical information from HFIS onto the residual system HS. Now, how do I do this precisely? I can use gauge fixing operators, which are just proportional to these rank 1 projectors onto my orientation states on R. So essentially, I just fix the state on R. And if I choose my normalization constant correctly, I will get a unitary from HFIS into the space where on R I just have this orientation state, and the factor on S is the system S as seen from R in orientation G. Okay, now let's use this setup with a quantum reference frame R and these gauge fixing projectors. Now, an important thing, an important first observation we can make is that if there is a set inside of my group, some G tilde, for which the orientation states are orthogonal, then the gauge fixing projectors onto the orientation states corresponding to this set satisfy the Knill-Lamp conditions. So these are correctable errors. Right? And this is essentially just a consequence of the fact that the inverse of the gauge fixing projectors on HFIS is this projector onto physical states. Okay, but how does this help us in finding the set of operators AQ that we wanted? Well, it turns out that if we additionally assume that G is abelian and that our reference frame is ideal, so that all the orientation states are orthogonal, then we can build such a set of operators AQ just from linear combinations of the gauge fixing operators. So we integrate over the conjugates of the characters times the gauge fixing projectors. So to conclude, we can identify gauge systems with quantum error correction codes, and then we can find such sets of operators AQ, which are correctable. And it turns out if our frame G is ideal, and if our frame R is ideal, and the group G is abelian, then this set comes from gauge fixing operators. And as a side note, this works even if the frame is non-ideal, if it is ideal for a subgroup. So if the orientation states restricted to a subgroup make this an ideal frame, then these operators A I get will map into coarse-grained charge sectors. So I can still apply this idea. Okay, now let's look at an example, namely, let's look at what this looks like in Lattice QED. Here I should also mention that this was a joint release with Lacambra et al., who also worked on a very similar topic. So if you're interested, this is the archive identifier. Okay, so some preliminaries. The setup of Lattice QED we're using is Hamiltonian Lattice QED. So we fix temporal gauge so that we can keep time as a continuous parameter, and then we discretize space. So we end up with a lattice with vertices and oriented links which connect these vertices. And then to get our kinematical space, onto every link we place one copy of L2 of U1. This I will sometimes also call a quantum rotor because it corresponds to the configuration space of a two-dimensional quantum rotor. So here, okay, we have our group position states, these e to the I thetas, and this operator U, which I will refer to as a link operator. I can also Fourier transform this to a state with definite electric flux, and I have this electric flux operator epsilon. Just briefly, how can I identify this with a standard electrodynamics if I go to a continuum limit? Well, I can just see the link operator as an exponential of the vector potential, and I see the electric flux operator as an electric field. For the magnetic field, I additionally need to introduce plaquettes, which are the smallest loops I can take on my lattice. So I have this plaquette. I define a plaquette operator as a product of link operators as I walk around this plaquette, taking inverses whenever I pass a link in its opposite direction. And then, well, you can see that the U is already an exponential of the vector potential. Then this will be an exponential of something like a discrete curl of the vector potential. So this will give me something like an exponential of the magnetic field, which is normal to the plaquette. Okay, so this is how Lattice QED works. Now, important for us is to understand what the the encoded physical data looks like, this HFIS inside of HKIN. And here, as in the continuum, once we fix temporal gauge, Gauss's law becomes a constraint. And so for every vertex, we get a constraint for Gauss's law. This essentially just constrains the electric flux going out of the vertex to be equal to the electric flux coming in. So this is really just a discrete version of Gauss's law. And the set of these constraints now generate my gauge transformations, which can be written as products of exponentials of these constraints. Now, in the future, I will assume that we have either periodic or smooth boundary conditions, which just means that every link is always connected to two vertices. So if I sum over all of my constraints, every link will be attached to one vertex in which it goes into and one from which it comes out of. So all of the constraints sum up to 0, which means, as a consequence, that we can see this group of gauge transformations as a representation of U1 to the NV minus 1, where NV is the total number of vertices I have on my lattice. Okay. Okay, now we understand the structure of lattice QED. Let's try to find quantum reference frames for this setting. And it turns out that quantum reference frames for a lattice gauge theory are given by spanning trees on the lattice. This was, for example, also used in this paper to calculate relational entanglement entropies. And the idea here is to use this big tensor product and split this into two parts, namely the links which are contained inside a spanning tree, which is a subgraph which contains every vertex but has no loops. And the rest will be my system S. Now, a spanning tree parameterizes the group of gauge transformation. And we've already seen that this is a representation of U1 to the NV minus 1. It turns out that a spanning tree has NV minus 1 links, so we can have NV minus 1 parameters lambda in our orientation states, which completely parameterize the gauge group, which makes R an ideal quantum reference frame. Yes? Yes, I think the best motivation I have is that once you gauge fix a spanning tree, essentially every holonomy on here is mapped to, okay, no, this is incorrect, but you can essentially write a set of generators for all the holonomies as a set of independent holonomies. And these are identified to the links outside of the spanning tree. For example, let's say we have this link here. This would be associated to the holonomy I get if I close the loop on the spanning tree. And if I gauge fix my spanning tree, this will map this holonomy to the link operator on here and vice versa. So this is just a way of fixing all the holonomies so that their degrees of freedom are exactly on one link outside of the spanning tree. Okay. Right, and because this is an ideal quantum reference frame, this means that our physical space, Hphys, is isomorphic to Hs. So it's isomorphic to this big tensor product over all of the links not contained in the spanning tree. And this can help us understand what the encoded data looks like if you see this as a quantum error correction code. So again, Hphys is isomorphic to a big tensor product of all of the links in S, which means that we essentially encode NL minus NV plus 1 quantum rotors into NL quantum rotors. Here, NL is the total number of links. So the structure I get here is something that's sometimes called a quantum rotor code. And so pure gauge lattice QED can be understood as such a quantum rotor code. Now, what kind of errors can this quantum rotor code correct? First, it's important to note that only gauge-violating errors can even be detected. So these are the only ones that we can hope to correct with these charge sector measurements. And it turns out for lattice QED that these gauge-violating errors are changes in electric flux. And these changes in electric flux on the links are realized by the link operators U, because these act on states with definite electric flux K by shifting it by m units. Okay, and now I have a quantum reference frame R, which is ideal, and I can apply the ideas from before, so I can, from this immediately obtain a set of correctable gauge fixing operators. I can combine these to a set of these AQ operators, which map into the different charge sectors. And if I do this, what I find is this set of correctable errors. Now, these are arbitrary products of link operators supported on the spanning tree, which means that electric flux shifts on the spanning tree are correctable. Alternatively, we can understand this set as being arbitrary products of Wilson lines supported on the spanning tree. And just so that we can get a picture of how this error correction works, let's imagine that we have some Wilson line of an error which occurs. Now we measure the constraints on every side. This will give us 0 everywhere except at the endpoints of this Wilson line, right? Where it will give us plus or minus 1 at the beginning and the endpoint. And now, because we are restricting to errors occurring on the spanning tree, this gives us a unique path connecting my two violated constraints. And I can then correct this error again. Okay, now this is only one set of correctable errors that I can have. I can also find other correctable errors if I take a different set of such AQs, which does not come from a spanning tree. For example, because this is a quantum rotor code, we can just use the fact that the U distance of the code is 4. And this is the minimal weight of any gauge invariant U-type operator, which is a plaquette operator. And the U distance being 4 means that any single shift in electric flux on a single link is a correctable error. Okay. Now, this was all for lattice QED in the pure gauge case. We can also include fermions into this model. And we can do this in the staggered fermion formalism. So we place fermions on even sides and antifermions on odd sides, which will change our kinematical structure. So now, instead of just having our link spaces, we also get this qubit-like degree of freedom on every vertex. These qubits are spanned by the occupation number basis, so I have zeros or ones depending on whether I have a fermion or an antifermion. And additionally, I get my fermionic creation and annihilation operators satisfying their canonical anti-commutation relations. Note that this charge density here also involves a term over here which just takes care of the staggered nature of the fermions. And now if we ask again what the physical states in here look like, these are again the states which satisfy Gauss's law, but now Gauss's law also includes the charge density. And again, this is just like in the continuum where the divergence of the electric field is equal to the charge density. And now to find QRFs for this model, including fermions, either we can use the spanning trees from before, which works just as well, or we can use the fermionic field to parameterize all the local gauge transformations. And the idea here is that we can use these states, lambda v, which have this relative phase e to the minus I lambda v. And if I act on this with this local gauge transformation, this will change the phase lambda v to lambda v plus eta v. So essentially what I can do is I can just tensor up all of these states to make my set of vertices R tilde a complete but non-ideal quantum reference frame. So this is complete because it can fully parameterize all of the local gauge transformation, but it's non-ideal because you can see that these states are in general not orthogonal. But similarly to before, we've just split the kinematical tensor product into a factor, which is our quantum reference frame, and a factor for our residual system. Okay, now again, in this model, we are interested in finding what the correctable errors for this system look like. And it turns out that on the one hand, we could correct all of the U errors exactly in the same way as we did before, but now that we are also including fermions, we need to take care of errors which affect the fermions on the sides. And the errors on the sides can all be written in terms of psi v dagger, or products psi v dagger psi v, or psi v dagger. Now the only unitary errors I can form from this are of this form. So they are linear combinations of a creation and annihilation operator with some phases. So these are the errors which I can hope to correct on the sides. for example, if I just fix my phase alpha to be 0, then this just gives me a poly X on a side. So this essentially swaps a fermion being there with a fermion not being there, and vice versa. And now I have this quantum reference frame, which is non-ideal, but for a subgroup C2 of U1, this will be ideal again. So I can still use the same idea from before, but now I will only be able to correct this error via coarse graining of charge sector measurements. And if I do so, the set that I obtain is this here. So I get a big set of all possible local flips in occupation number on every site, which is correctable. So this RV is either 0 or 1, indicating whether this error happened or not. And again, let's illustrate this. So let's fix for now the case that AV alpha V is equal to 0, so that this AV is just a poly X. And then if this X affects some site, and we go and measure the constraints, well then here on this side we cannot say whether we measure the constraint being +1 or -1, because this X maps a state in H phase into something which might lie with within the charge sector which has a +1 or a -1 violation here. So it maps into a coarse-grained charge sector where we just know that the absolute value of the constraint is 1. So what we need to do is we need to perform some coarse-grained coarse-grained constraint measurement. But if we do this, we can still find every site which is affected by such an error as the site where our constraints lie within this coarse-grained charge sector. And then, because I've already fixed alpha V to be 0, I can correct the error again. And last but not least, I can combine my ideas from before with this idea. So I start out with a coarse-grained charge measurement, which will detect whether there has been an error AV. And if there has not been an error AV, but I get violations on two adjacent sites, I know that an error UL must have happened, and I can go and measure the fine graining of the charge sectors to find out what exactly the power here was. And this combination makes single number flips of the occupation number or electric flux shifts on any link or any site correctable. This is, by the way, a generalization to U1 of a result which was previously shown for C2 lattice gauge theories in the context of getting fault tolerant schemes for quantum simulations of lattice QED. Okay, and now let's recap some of the lessons learned. So the first and most important lesson is that we can understand gauge systems as quantum error correction codes, and quantum reference frames, on the one hand, yield insight into the code structure because they give us insight into what the encoded data looks like, and they give us a set of correctable gauge fixing errors. And this is true whenever we have a compact gauge group, whether it's Abelian or not, or whether the quantum reference frame is ideal or not. But if our gauge group is Abelian and the quantum reference frame is ideal, then we can obtain from the gauge fixing operators such a set of errors AQ, which map into the different charge sectors, which are correctable by this charge sector or syndrome measurements. Then for lattice QED, we can find quantum reference frames from spanning trees on the gauge field, and these all yield us families of correctable errors, which consist of electric flux shifts on the spanning trees. And similarly, if we include fermions into our model, then the fermionic field quantum reference frame yields a set of correctable errors, which are occupation number flips on each site. Now, where may potential applications of this all lie? Well, one of the most active areas is lately has been efficient fault-tolerant simulations of lattice gauge theories, which was started by this paper by Rajput, Rogero, and Wiebe, and has recently gathered a lot of interest because it turns out that if you use Gauss's law for quantum error correction via these charge sector measurements, you can get rid of a lot of overhead if you were to encode your data in a more standard quantum error correction way. And another application, which might be interesting, is we can use quantum error correction toy models, which exhibit certain properties for gauge systems to analyze these gauge systems. So this has like quantum error correction code. Toy models have already shown to be useful in other topics like holographic codes. But this could give a way to generate broader toy models. And lastly, a connection between these two topics can help us import tools from one side to the other. So we can either try to understand gauge theories via tools from quantum error correction, or quantum error correction codes via tools from gauge theories. Okay, and with this, thank you for your attention, and I'm looking forward to your questions.
Okay, thank you so much for such a nice talk. Are there questions? Okay, I have to think about the questions.
I'm not sure this. But anyways, so you started talking about stabilizer codes at the beginning.
Yes.
And then I didn't understand if what you talked about afterwards was just a subset of stabilizer codes, or this can be extended in general, like whatever symmetry you have, you just look at a subspace and so on.
This is more a generalization. So usually stabilizer codes are formulated for qubits, and then your stabilizer group will be a subgroup of Pauli operators. And this is then sometimes generalized to qubits, QDITs in D dimensions, and sometimes to U1 systems. But this is really more taking this idea and using it for any symmetry group. Yes.
Yeah. I have an even more stupid question. So just I wanted to understand the connection with the previous literature on error correcting, and also how it connects to the rest of theoretical physics. So in general, like, is this, so you mentioned a few times that the errors you can correct are gauge violating errors. So I guess this is not things that are actually happening in Lattice QED. And so that's one part of the question. And second part of the question, in terms of error correction, like, is sort of, if the answer to my first question is no, are these Lattice QED inspired circuits something that people working on quantum computers use? Like, what's the relation between?
Okay, so the answer to your first question is that, okay, in electrodynamics, of course, these errors do not happen in nature because, okay, they're gauge violating. But what's of interest for practical purposes is simulations of Lattice QED. Do you want?
Right, so if you're doing a simulation and one of your qubit flips and it's like out of...
Exactly.
It's like it's not representing anything physical anymore, you can bring it back.
Exactly. Yes. And then, exactly, you can use Gauss's law constraints to correct these errors.
Right, very cool, thanks.
Yes.
I was thinking, because stabilizer codes can be classically simulable, and I wonder, like, here, are we analyzing just like a classical, I don't know, is it like a classical part of QED in some sense, quote unquote, or?
So okay, I'm not 100% sure about my answer here, but I think so, because this is all just, at least for the pure gauge case, it's all just U-type stabilizers, which would be like a classically simulatable code. In the case where I include my fermions, I'm not sure anymore, because there I'm somehow mixing U1 systems and qubits, so it's some sort of a hybrid. So there, I'm not sure.
Another question is, like, I'm more familiar with like the toric code, but you mentioned some other code, like what, rotor, something like that?
Yes.
Like, well, what is it? I have no idea.
Okay. The idea of a quantum rotor code is essentially if you take stabilizer codes and you take the QDIT D to infinity limit and you replace these CD spaces with L2 of U1s. And then your stabilizers are either like U-type stabilizers like here, or you can also have like exponentials of these epsilons as stabilizers. So just a formulation or a generalization of stabilizer codes to U1 systems.
Are there more questions? I want to add just a brief comments on the errors happened in nature. It might be constraint violating. And this is actually an open field that's very worth investigating. And for those constraint violating errors that can be expressed as this gauge fixing operator, in this way, there is a scheme of how to correcting them.
Like, are quantum computers going to be better at lattice QED than classical computers?
That's a good question. I'm not nearly practical enough to have an answer for this.
Yeah. Okay.
Though I would suspect so. But yeah.
You could imagine you could like set the interactions between the qubits to be like somewhat something like a QED, and then you just let them go for a while, and then you measure them at the end. But who knows?
Yes, I mean that's the idea of these fault tolerance simulations, is that you actually simulate lattice QED, and you use Gauss's law for one part of the error correction. So okay, here you can only correct U-type errors. Maybe if you truncate this will translate to only being able to correct X-type errors. But then you can concatenate this, maybe with a repetition code for the other type of errors, so that you can really have a fault tolerant simulation. This is the idea, the first idea in this paper here.
Okay, if there are no more questions, let's thank ELIAS again.